Hi guys, welcome back to another video. Today we will be going over logarithmic differentiation. The logarithmic differentiation is especially useful when product rule, chain rule, quotient rule sometimes can work. Like in this case, we can take a quotient rule with a product rule, but it'd be long, mundane, and really time consuming. And so we can take we could use logarithmic differentiation. Another way we can do this is when it is not possible to differentiate through product, quotient, or chain, such as x to the x, because we got an x in the numerator, and we can't take we can't take a power rule there. But to start off with this question, with this question right here, so to start off with logarithmic differentiation, we simplify f of x to y, and we take the ln of both sides. Ln of y is equal to ln of and so through logarithmic properties we can rewrite this as the top minus the bottom, or these two bottoms in this case. So ln of y remains unchanged, and we take ln of x to the fifth minus ln of the first term on the bottom minus ln of the second term. And for the second term, we'll just rewrite this as a exponent instead of a square root, because it's easier to differentiate that way. And so we end up with right. And another way we can actually simplify this, make it easier for ourselves, is taking these two exponents and just moving them outside through another logarithmic property. And so from here, we take the derivative, essentially. We take d dx of both sides. And so it is important to note that ln of something is just 1 over that thing, if it's a variable. So we take that derivative in ln, so the derivative here would be 1 over y, and through implicit differentiation, we have a chain rule of dy dx, which is, apologies, which is exactly what we're trying to find in this case. So that's great. So when you do this, we have 5 on top over x, because when we take the derivative of x, it goes to the bottom, minus, here we actually have a chain rule because there's a negative 10x. So we do 1 over 10, 1 minus 10x times 10x, 10, sorry, minus 1 half, once more right here, 1 over x squared plus 2, we have a chain rule, times 2x. And so, from here, what we actually do is we multiply the y over, and we already know what y is. In this case, y is this original function. And so, dy dx is actually equal to, parentheses, 5 over x minus, or plus 10 over 1 minus 10x minus 1 over 2, 2x, those two cancel out, so I'm going to cancel those two out, x over x squared plus 2 times y, which is the whole function. So and that right there would be our derivative of our original equation. Now, it's not really pretty, but this is a lot more convenient than, say, taking a product and quotient rule, which you would have to do if you were to try to use product and quotient rule in the original case. Now let's go over a certain scenario where we can't exactly take a quotient rule, we simply can't because we have an x and the exponent. So if you can find f of x to be equal to x to the x, since we have an x and a variable in the exponent, we can't take a power rule, and thus power rule, quotient rule, product rule, all that does not work. And so to differentiate this, we start off once again taking the ln of both sides, x to the x, and once again we can bring that x out. So ln of y is equal to x ln of x. Now when we take that derivative, we will have a product rule right here. And so when we take that derivative, once again, 1 over y times dy dx is found through the chain rule, implicit differentiation. And when we take that product rule, we get ln of x plus 1 over x times x. That just goes to 1. So what we end up with is dy dx is equal to ln of x plus 1 times x to the x. I hope that this made sense and it was helpful. Logarithmic differentiation is just another way of taking a derivative that is either much too complex to really take an ordinary way, so we just invented another way to take it. And it's actually extremely useful because we have all these things that we can do now with a variable and the x component right here. But yeah, that's logarithmic differentiation. I hope you enjoyed.